Looks like we're live. Hello everyone and welcome to yet another recreational programming session with Mr. Zozin. Hello everyone. I can see you guys in the chat. Welcome. So let's make a little bit of an announcement as usual and officially start the stream. So this is going to be a red circle live on Twitch. And what are we doing today on Twitch.television website? Today we're doing hash tables in C. That's right. I'm gonna give the link to where we're doing all of that, twitch.tv/turning. I'm gonna ping everyone who's interested in being pinged, and there we go. The stream has officially started. So, why am I implementing hash tables in C? No particular reason. I just felt like it, right? So I was watching the software development section on Twitch, and one of my good friends, Provat, right? So I really recommend his streams, by the way, twitch.tv Provat. All right, he's doing Russian-speaking streams, but he also speaks English, right? So if you accidentally stumble upon his streams, just say hi, right? So, and ask something in English, he will answer anything in English. And so he's working on actually adding support for ray tracing to Half-Life 1. So maybe this is something that you could be interested in, right? But it's very technical. He's not really focused too much on entertainment. He primarily focused on actually delivering implementation features. So keep that in mind. He speaks two languages, Russian and English, whatever you prefer. So when he was working on implementing a hash table, right, for caching textures or something like that, and that just like kind of tickled my nostalgia a little bit, right? Because the hash tables, implementing hash tables from scratch kind of reminds me of my childhood when I was only learning programming. I was learning, algorithms and data structure, and it's just like, holy shit. I haven't implemented a hash table for quite some time already, So, so let's go ahead and maybe do that. And we probably need hash tables for one of our existing projects, right? So specifically for Visualizer. All right, so in the Visualizer, we have a very simple sort of like an asset manager, right? So essentially, which allows you to do things like asset load. I don't remember. I think it was like a load texture. Yeah, assets texture. So essentially, if you need a particular texture, you can do the following thing. You could say assets texture and the path to that specific asset, and what it will do, it will load this entire thing once, and then cache it. But right now it caches it into linear associative array, right? So inserting into that is basically O of 1, but searching is O of n, which is fine as long as we don't have too many resources. But maybe in the future we're going to have a lot of resources, and this is where we can apply our hash table. Right, so maybe in the future it's also going to be useful. It's not the pressing issue right now, but thinking for the future. So yes, so let's go ahead and maybe create a folder where we're going to do all of our experimentation. So I'm going to do C hash table, right? So C hash table, and let's go inside of it. So, and let's create a file. Let's start with a good old hello world. A hello world. So I'm gonna just do the usual thing. And I suppose since we recently started to very actively use Nob, I'm gonna create the Nob build right away in here. Right, so let me actually go to Visualizer and straight up steal this file. Yes, I am still in code. I'm straight up still in the code, but I'm still in my own code. So that's fine. So let's create Nob C, which is going to be the program that builds this entire thing. We're going to include the nob.h, and we're going to define Nob implementation, and let's actually create an entry point, right? So essentially, we're almost like writing the good old build sh, but in C. Imagine if they, if build sh was written in C. So that's basically what we're doing, right? It's just like build sh, but better, right? Written in an actual programming language, not a toy programming language, but an actual real programming language. So, and essentially one of the things we want to have is Nob go rebuild yourself, right? So let me quickly open it. Nob go rebuild yourself. So this is a very important macro, it's an extremely important macro because it allows you to like not rebuild the executable of the build system every time you modify it, right? It's capable of actually automatically detecting that it needs to be rebuilt and rebuilding itself, right? So that's what it's capable of doing. So in here, let's actually create a command line, right, which is going to build the main application. So we're going to do a Nob cmd append, right, and we're going to append in here what we're going to be building with cc. So that's the compiler. Let's enable a couple of flags, maybe WAll for all of the warnings, maybe some extra warnings as well, maybe some debug information, because it's quite nice to be able to go with the debugger and stuff like that. Maybe we're going to be super pedantic about the standard, who knows. I think it's a good idea generally. So after that, we're going to specify the output file path and the input file path, and we're basically good to go. So the only thing we need to do Nob cmd run. I think this time we're going to run it synchronously, right? So we're running it synchronously. In case of an error, we're going to return non-zero exit code, and there we go. We made a simple build system, right? So we need to the only thing we need to do is to bootstrap that build system. So let's just build it as it is, nob.c. Right, so there we go. So something went wrong in here. So you're supposed to provide, I thought it doesn't have to be a point, I suppose, right? So yeah, it doesn't have to be a point. Okay, so we bootstrap the build system. We don't have to rebuild that file ever again. So that's very important. It's not like you have to rebuild this entire thing every time you modify it. No, you don't have to rebuild it. So you can just run this entire thing and it builds your main application. Right, so if you want to, for instance, after you essentially compiled it, run, if you want to run it, so the thing you can do is essentially just like this, main, and just automatically run, right? So you build it and automatically run it. Look, I don't rebuild the main thing, and it tries to compile itself automatically, and as you can see, it rebuilds itself, then it rebuilds the main program, and then it runs the main program. So that's how cool it is. It's not like you're constantly fiddling with your compilation or anything like that. No, you bootstrap this build tool once and it takes care of everything itself. You don't have to worry about that anymore, right? So you just sort of like pre-compile it and you forget about it. You just focus on making sure that your main application builds and stuff like that. It's just like you don't have to worry about that. And it doesn't rebuild itself, right? So as you can see, the second time it doesn't rebuild itself because it didn't detect any new changes, right? So that's basically what we have in here. So that's how cool it is. Isn't it cool? I think it's pretty freaking cool. So this is called Nob, which is short for no build. Okay, so what kind of problem do we want to solve with hash tables? What kind of problem? So the classical problem that I like to use is essentially counting words within the file, right? So essentially, let's take some file, some text, you know, split it by words, somehow tokenize it, doesn't really matter, and then basically count the frequency each individual token, right? So that requires having a hash table, right? Because you basically need to remember whether you already saw a particular word. You need to use the word as the key, and then every time you encounter that specific key, you need to increment the counter, right? So it's a very good sort of like you know, a problem to test hash tables on, I think. Maybe not, right? So I'm not a you know, computer science person. So let's actually find the Shakespeare file, right? So Shakespeare txt. So the classical file that is usually used for testing some linguistic stuff, or maybe in, artificial intelligence stuff, machine learning and stuff like that. Shakespeare.txt. Right, so this is the file. So I suppose I'm gonna actually put this file in the chat if you're interested, right? So it's a relatively big file, actually. So it's like 8 megabytes, I think. Right, so I'm gonna go ahead and just download this thing. So it's actually 5.3 megabytes. Is that full? I remember the last time it was actually 8 megabytes or something, but I suppose, I mean, 5.3 is, well, I mean, like, look how many lines it has, right? So it's pretty big, right? So imagine, like, I think this is the entirety of the work of the Shakespeare. I think this is the entirety of the works, right? So, and just think about it. The work of a life of a like great writer can fit in 5.3 megabytes. How much garbage ChatGPT can generate in minutes? It's just like, it's so mind-boggling, right? It's so mind-boggling what kind of stuff we can achieve with computers. What about War and Peace? How much does it take, actually? I don't really know. We could use War and Peace, but I mean, it's in Cyrillic, so we have to deal with UTF-8. So it's just like easier when it's all in ASCII. It's easier when it's all in ASCII. Plus, I suppose not that many people in the chat speak Russian. I suppose some people speak, but I mean, not everyone. Alrighty, so we've got this thing. So the cool thing about Nob is that you don't have to use it in the build script. You don't have to use it only in the build script. You can use it in the main application as well. And in fact, Nob itself has a lot of useful utilities that you may want to use in the main application as well. So it's sort of like a framework that you can use for just building C applications. Yeah, maybe I should turn it into some sort of like a framework. People like frameworks. So we have a thing called read entire file, right? So read entire file, and it just reads the entire file into the memory, and that's precisely what we want in here, I suppose. So here we're gonna have a file path, right? So this is gonna be const char file path. And so what's the file path we have in here? So it's that one, and we're gonna have the content, le content. So let's actually call it something like content. So this is going to be allocated on the stack, right? But I mean, on the stack we're only allocating the you know, 3 fields: count, capacity, and the data pointer, right? So we're not allocating the whole buffer on the stack. So that's the only thing we're allocating on the stack. So, and just items points to a place allocated in a heap somewhere, right? So just because we place this thing on a stack doesn't mean the whole thing is going to be on the stack, right? So we read the entire file in here. If we couldn't do that, we right away return with the non-zero exit code. But in here we have the content, right? So here we have the content, and we can log some stuff in here. So size of S is ZU bytes or something like that. And then here we can say file path, content, count, and let's actually run this entire thing. So content unknown type, and this is because we need to include nob.h, right? So we're just including nob.h, and we're defining nob implementation. So is it going to work? So this has to be a pointer. I do agree with that, and this requires you know, the logging level. And there we go. So the size of this entire thing is yeah, it's basically 5 megabytes, right? So this is 1.3, and this is 5.4. Right, maybe even 5.5 if you round it up. So yeah, that seems to be working. So the next thing we need to do, we need to tokenize this entire file. So the question is how we're going to be tokenizing this entire stuff. We can just split everything by, you know, by spaces, and maybe that's a sufficient enough tokenization, right? So let's give it a try. So essentially, while content, maybe it would make sense to. Yeah, so we need to have like a string view, nob string view. Right, so the difference between string builder and string view is that string builder owns the memory, right? It owns the memory, but string view just points at the memory, right? It doesn't own it. It's sort of like a lightweight. It doesn't manage the memory or anything like that. And in fact, if you take a look at the implementation of this entire thing, it only has the count and the data. It doesn't have a capacity because it doesn't manage capacity. If you take a look at the nob string builder, it does have a capacity because you can push into that thing and expand it, right? You can then expand it. And we want to basically construct this entire stuff, but I already call this thing a content. So maybe let's call it buffer, right? So because it owns the memory that was allocated in here, and the content is going to be this thing, right? So, and let's actually find the string view. So here, the data is going to be the items of this buffer, and the count is going to be the count of this buffer, and there we go, we have a string view. So, and while the content count is greater than 0, we can basically chop by a space, sort of speak. We can chop things by a space. So essentially we can do nob sv chop by delimiter. So we provide the content and we provide the delimiter, which is the space. And there we go, we got a line, nob string view line, not really line, right? So let's call it a token. And the next thing we can do, we can just print that specific token, right? So let's do nob log, nob info, and we can just put something like this in here. So I think I need to do it like that, sv fmt, sv arg, and this is going to be token. And that's about it. So there will be a lot of tokens in here, actually. So maybe what we want to do, we want to kind of limit how many tokens we want to print there, right? So how many of them we want to print. So this is going to be 4. Right, so let's actually do something like, let's print first 10 of them. Right, so ++i. Okay, so let's go ahead and just try to run this entire thing. And as you can see here are the first 10 tokens that we've got in here. We can even maybe put a little bit of a space in front of them just to separate them from the rest of the output, but there we go. So with Nob, programming in C feels like programming in Python or something like that, right? See how quickly I just like iterate with my code. I really love that. I really love that. So and there we go. So we iterating over all of the tokens in here, right? So we can take a look at the first 100 of them. Right, so some of them even contain, you know, new lines. We're using only space as a separator. So I didn't think this is a particularly great tokenizer. I don't think this is a particularly great tokenizer. Maybe we want to come up with something better. So splitting just by delimiter space is not particularly great idea, I think. It is not particularly great idea, so what we have to probably do, we want to be able to split just by space, which is essentially, yeah, any of those things. So if we take a look at how Nob is implemented, right, so we do have, for example, trim, Nob sv trim, right, so, and trim actually trims off everything that is a space, but we don't really have chop by space. Maybe it would be nice to introduce like a new function in here that would be called chop by space or something like that, or maybe chop by predicate. I remember the original library that I from which I ported this entire stuff. I think it had a special function that accepted the predicate. Right, so it accepted some sort of a predicate. We can actually take a look at it. We can actually take a look at it. So, of course, we're talking about web applications. So sv chop by, there is chop by another sv, but I don't see the predicate. So there is a chop. Oh my god, why is it jumping around? So we have chop by sv, chop by delimiter. So there's no original chop by a particular predicate. There is a chop like while a particular predicate, which is not entirely what I want. Right, so maybe what we're gonna do in here is introduce like chop by space, which is probably a common case in here, right? So you do want to chop by a particular space. So let's actually find the implementation of chop by delimiter, right? And let's simply copy paste it. I don't think we need to think about that too much. Chop by space, we do not accept any delimiter in here, and instead of comparing this entire thing, right, so we're gonna do is space like so, while it is not is space, and as you can see we just have implemented this entire stuff, and then I'll be able to copy paste this entire stuff back into the original repo. Right. Okay, so chop by space, and space is anything that is actual space, tab, new line, carriage return, and stuff like that. All of that is considered space, so we're going to be splitting by that. So interestingly, maybe one of the things we want to do first of all is to trim, like remove all of the spaces in front, so the like any amount of spaces between the tokens are fine, right? So something like that. So sv trim left, right? So it's a pure function, right? So you have to reassign this entire stuff like that, and then you chop by space, and then you print it. So that way it will not create these things that have new lines in them and stuff like that, hopefully. So let's actually give it a try. Okay, so let's take a look at 100 tokens in here. And as you can see, everything is on a single line, right? And it doesn't matter how many spaces we have between them, so everything is pretty, everything is good. I kind of like that. I kind of like that. So what about first 1,000 tokens? Here are first 1,000 tokens. That's pretty cool. That is pretty cool. Okay, so what would be sort of like the first approach to counting the frequencies for the of words, of tokens, or something like that? It would be to have some sort of an associative array, right? It would be to have some sort of associative array, and it's basically going to be an array of cells, right? So array of key values. So maybe we're gonna call it frequency key value. And in here, we're gonna have a Nob string view key, right? So this is the key, this is the value of the token. And then we're gonna have the value, which is the frequency. So, and then essentially the associative array is gonna be array of these sort of like a cells, you know, frec kw. So frec is frequency. So how can we, you know, do that? So usually I define associative, like dynamic arrays as a separate structure where the items are the, you know, the cells that you want to have, and then you have a counter and the capacity that keeps track of everything. And how would we call this entire thing? How would we call this entire thing? So maybe, you know, stat, right? Something like stat. Or maybe quite often I just call them S, as, you know, the plural, right? So usually I have this some sort of a convention when I define a dynamic array. I just call it the type of the item plus S to indicate that there's several of them. If that makes any sense. So there is a frec KW, a KV, and this is a frec key VS because there is several of them. Right? Does it make sense? Maybe. I don't know. And essentially what we can do, we can just define this entire thing. So frec kvs, and this is going to be just frec, and when you you know, initialize it like that, it's going to be completely empty. And then with a special macro, we'll be able to append new things in here. Like we're going to be able to append new things in here, so new kv, and it's going to automatically expand this entire stuff. Is going to automatically expand this entire stuff and you know, allocate the memory and everything. So let's actually go ahead and do that. Let's actually go ahead and do that. But one of the things we need to be able to do, we need to be able to do search, right? So we need to be able to do search. Let's actually create some sort of a function. I don't really know how to call this function, but it's going to return a pointer to frec kv, right? So we can call it like a find key. I think we've already done that in mutualize the associative array, but we can implement it one more time. Right, so in here, we're gonna accept this entire thing. It doesn't really have to be by pointer, right? Because we're not gonna be modifying it. And the key is gonna be Nob string view the key. There we go. So here we can just go and, you know, linearly search for this entire thing, right? So, and I wanna implement like a very slow linear approach just to see how slow it will be when we want to you know, analyze all of the tokens you know, within the file, within 5 megabytes file. Actually, interesting question, how many tokens we have at all? Right, so how many of them we have at all? So let's actually not print them, and let's remove the limitation in here. Let's remove the limitation. Maybe we can even move this thing outside in here, and that I becomes basically how many tokens we have, right? So maybe we can even have something like count, and this is the count, and then we're gonna do nob log, nob info, and we're gonna say S contains ZU tokens, file path contains count tokens. And let's actually try to run this entire thing. So we have almost million tokens, 901,000 tokens. So this is how many we're going to analyze. And how long will it take to actually analyze the frequencies using linear search? Using linear search. That's very interesting. So we have a couple of warnings in here, but this is because we haven't used variables and stuff like that. But I mean, who cares? Who cares? Who cares? Who cares? Okay, so let's actually try to find this entire thing. So we're going to be doing frac count plus I. And in here, frac items I. And we want to take a look at the key. So as far as I know, in Nob, we have something like Nob SV equal, right? There we go. So there's literally equal. We can check for equality of this entire stuff. If the key in here is equal to the needle key, right? So this is the needle key. So there is some sort of like a really interesting naming convention, at least in old libraries in all languages. When you have a find or search function and you're searching for something, usually the thing that you're searching is called needle, and the thing within your searching is called haystack. So yeah. Yeah, so chat knows that. Chat knows that. For the first time, I think I saw that in PHP. I think I literally saw that in PHP. So in the PHP like standard library, throughout its API, this is the naming convention that exists there. But then I saw it in some other places as well. So yes. So if we found that specific thing, what we can do, we can simply return the pointer to this thing right away and stop the search. And then if we couldn't find this thing, we just return null. As simple as that. As simple as that. So, oh yeah, I changed the naming. So now I have to rename frac to haystack. So this is the haystack. There we go. And that should work. That should work. There we go. So everything seems to be working. Okay. So how are we going to be analyzing all of that? So first we need to try to find. So find the key. We provide the frequency and we provide the key, which is the token. So, and that should give us the frac kv. So it should give us this pointer. If we found kv, if kv exists, the only thing we need to do, we probably need to just increment the counter within it. Right, so within we have a key and value is the counter. It is the counter. If we couldn't find this entire thing, what we have to do, we have to just create a new one, right? So let's create frac kv, a new one, but I probably, let's call it new kv. And the key is going to be the token, and the value is going to be 1, because this is the first thing that we encountered in here. And then we can just push this entire thing, nob da append frac new kv. Frac new kv. And maybe we can even do a little bit of a trickery. Here's a little lesson in trickery. So, and I suppose since we have you know, commas in here, we probably need to put parentheses around this entire stuff. So yeah, that looks good. That looks good. So let me just go ahead and only build this entire thing, so I can just comment out this thing and run it, and it will only build it in here. So we're finding a key, so we don't have to really provide a point in here. We have to do it by value. There we go. So it's kind of convenient how within the build script I can just do that, right? And it will work. It will work. Maybe we can have some sort of a subcommand in here, right? So basically, if you just do nob by itself without any argument, it will just build it. But if you do nob run, it will also run it on top of building it. So we can quite easily do that. So essentially, if first of all, we need to probably get rid of the program in here. So const char program nob. What is it? Shift args, argc, argv. So that just creates a program, right? Because the first argument here is program. And then in here, if argc is greater than 1, right, if it is greater than 1, what we want to do, we want to take the argument that we got in here, argc, argv, and this is going to be basically the subcommand. So this is our subcommand. If the subcommand strcmp subcmd is equal to run, we just run this thing, Otherwise, we probably want to do something like nob log, nob error, unknown subcommand, right? So we just want to say unknown subcommand s, and we just provide the subcmd in here, and we return on 0 exit code. There we go. So if I just do nob, it just builds it, but when I do nob run, it should also run it, but if for some reason it didn't freaking run it, what the fuck is going on? Excuse me, I forgot to put equals 0 in here, freaking C! 2023, we're still using this goddamn freaking language. Anyway, so yeah, there we go. So as you can see, it still doesn't fucking work. Fuck you, Leatherman. So what's up with that? I don't understand. If argc greater than 0. So this is on me this time. Ah, there we go. This is on me this time. Look at that shit. It's still going strong. Right. I wonder, like, is it gonna take too much time to do this kind of thing? I wonder. Let's actually come up with maybe smaller files. Is there any smaller versions of these things? Sorry, page request was not found. We can create a smaller version of this file. Okay, so Shakespeare small txt. So we're gonna have a small version of this thing. And what's gonna be the small version? So maybe I'm gonna just go down 1,000 of times, maybe until the end of one of the works. That's a lot of shit. What the fuck, bruv? When will you stop? Right? Where's the end? Excuse me. Holy shit. Okay. Oh, okay. So I think I found it. Okay. So I'm gonna just copy paste this one. I'm gonna save it. So this is a small version, which is not even 1 megabyte. So it's 112 kilobytes, right? So to be fair, I think we need to be able to provide the file path through command line arguments of the main application, right? So this is what we have to do in here. Okay, so let's actually start doing this kind of thing. So this is going to be the argc char argv const char program, and we're going to do the similar thing in here. So nob shift args, right? So we're shifting the args. So argc argv. So that's what we're going to have in here. If argc is less or equal than 0, we need to complain, bruh, provide file path, nob log, nob error. So we have to say no input is provided, so then we're going to do nob in log, nob info. So here we're going to have usage. This is program, and this is the input txt. So this is going to be the program. I'm going to return this kind of thing. So afterwards, what we have to do just nob shift args argc argv. There we go. So let's just build this entire thing. So what do we have in here? So this is A. Okay, so it seems to be building, but then I want to be able to actually provide the arguments through run, right? I want to be able to provide the arguments through run. And I suppose one of the things I can do in here, I can just like append all of the rest of the argvs in there. But I think I can do a very cool thing, actually. I think I can do a da append many. Right, so last time when I was actually playing with this kind of thing, I forgot that I have this thing. So I could do cmd argv, argc, and it will just append all of them in there. So all of the arguments are going to be, you know, put in there. Let's actually try to do that. So there we go. And if I do run, it says no input is provided, but then I can try to provide the input, which is a Shakespeare small, And as you can see, it worked out. It just worked out. So it basically proxied this argument towards main. Right, it proxied there. Like I'm looking at how you work with Nob, and I'm actually surprised how fucking cool it is. Like, it's so ergonomic all of a sudden. It's so fucking ergonomic, it's so cool. Right? What the fuck? Okay guys, so this seems to be working. So now if I do a big file, right, it's going to take some time. As you can see, it's pretty slow. It is pretty slow by itself. You know what would be cool to have a Nob? An ability to measure time, right? An ability to profile things. Right, is this something that we want to have in Nob? Right, because one of the things I want to be able to do is to just say, okay, Shakespeare, small, and also print how much time it took to do all of that stuff, right? So, and maybe one of the way we can do that is essentially something like begin profile, right? Begin profile, and then like end profile, and it will print the time. And essentially what it should do, it just need to take the current clock value, right? Then on the end another clock value, and just subtract one thing from another. Right, and right, print the amount of seconds and stuff like that. So let me try to. We need to print some stuff in here, right? We need to make sure that we actually got what we expected. So with a dynamic, basically associative array like that, it is super easy to just sort it by the count. Right, just sort it by the count. We can simply do qsort, right? So we can simply do qsort. So let me take this entire stuff. So that should be pretty easy. And maybe what we're gonna do, we're gonna print top 10, right? Top 10 most frequent tokens. I think it makes sense. So what's going to be the base? Freq items, right? The amount of items is freq count. The size of a single item, is size freq kv, but I don't like it to write it like that. What I like to do is essentially just take this and take size of the first element. That way, if I modify the type of this entire thing, I don't have to modify this code, right? It becomes independent from the type. And in here, we'll have to implement the comparison function. So let's actually call it compare freq kv count specifically, right? It's going to be comparing the count because we're going to be sorting by count, right? So it's going to be compare freq kv, and here we're going to have A and B. All right, so here we have just pointers to all of these things. So let's actually say, let's actually cast them to something else. So AKV, and we're gonna just assign it like that, and BKV. Okay, so what you're supposed to return, this is actually very interesting. So how you're supposed to return this entire stuff. Let's take a look at the documentation of qsort. They actually tell you how it's supposed to be. Compare the comparison function. Okay, so let's actually take a look. The comparison function must return an integer less than, equal to, or greater than 0 if the first argument is considered to be respectively less than, equal to, or greater than the second. Right. So this is very interesting. And essentially, why it is done like that? Why it is done like that? It is done like that to maintain this sort of semantic. Imagine that within somewhere, within the sorting code, they do the following thing: A, B, less than 0. So essentially, you have to put the sign in here, the same sign in here as you would put in here if you wanted to compare these two elements. If you want to check that A is less than B, well, you put the sign less. You just sort of mentally move that sign inside. If you want to check that A is greater than B, you do it like that. And if you want to check if they're equal, you do it like that. So it is done like that so you can mentally sort of move them inside and put it between these elements. right? And why do we have to do it like that? Well, because C is an old language that doesn't have a operator overloading or any closures or anything like that. Like, yeah, so it's a pretty common way of doing that. But this is sort of like a mnemonic that you can remember, like every time you have to work with these kind of comparison functions. And to be fair, this is not only C. I think in a lot of like modern languages kind of have a similar paradigm, right, where the comparison is basically like an integer, which can be negative, 0, or 1. I think even Rust have something like that, but maybe Rust just introduced ordering type or something like that. JavaScript even does that. Right, so yeah, it's not very specific to C per se, because C is old, haha, old language. You can encounter shit like that in other languages, right? So this kind of knowledge is kind of transferable to other languages too. Most of them, okay, very interesting. I wonder how Rust exactly does that. Rust up. So in case of a Rust, I think it's just simply, you know, interface, right? It's simply an interface, which you have to implement. But I have a feeling that it literally had like a either ordering type, ordering. Yeah, okay, so they literally have like an ordering type, which is less, equal, or greater. And then there's also this CMP thing, right, that can return. Okay, so this is how they basically do that. So there's a CMP, so this is type of ORD, and you have to do it like that. Okay, that's very interesting. So, but the values of the underlying values of less, equal, or greater are not what they are. Okay, that's very interesting. What if we take a look at I32? Right, if we take a look at the primitive type I32, and it should have the ORD implementation. I'm pretty sure about that. So here's its ORD implementation. If we take a look at the source code of ORD implementation, how is it implemented? Okay, so it's probably okay, they're using some sort of a magic, or maybe it's, yeah, it's probably auto-generated from this macro, and the implementation of this macro is probably, oh no, here it is actually, here it is. So here's the implementation of this macro specifically, and what they do. Okay, so in case of primitive types, they don't even do any subtraction, right? So they just literally compare less, equal, or otherwise greater, right? So they just do that manually. How you do that in C, right? So how you do this kind of stuff in C? Well, if you want to achieve the same effect, right? So essentially, if A is less than B, that means the final value must be less than 0. How can you achieve that? Well, you can just subtract B from A. And that way, if A is less than B, it's going to be less than 0. If A is greater than B, it's going to be greater than 0. And if they're equal, it's going to be 0. Right, so in our case, we have to do, first of all, like A KV count, right, so B KV count, and we need to cast both of them to signed integer, but the idea is basically the same, right? In C, this kind of stuff is done by just subtracting the second one from the first one, right? In Rust, they wanted to maintain the type sensitive so hard that they have to do this manually, they have to check all of these cases manually, which may potentially result in more CPU instructions, because here what you have is a single CPU instruction, which is just subtraction. Right. So here, for idiomatic reasons, they have to do it like that. But maybe LLVM optimizes it to something better. And I don't know, maybe comparison and stuff like that is faster than subtraction. Like, I'm not a low-level person. All right, so who knows which one is faster? Who knows which one is faster? It probably gets optimized out. Probably. Maybe all of that stuff gets, first of all, inlined into the actual code and then already optimized sort of in place, considering the context and stuff like that. Isn't comparison just a subtraction? That's a good point. Yeah, it is, actually. So yeah, so here we also have a subtraction effectively on the level of CPU. So I guess that's fine. Not criticizing Rust code or anything, just comparing different approaches and stuff like that. Just comparing. But in fact, we actually want to sort in descending order, right? So by default, this is going to be ascending order. We want to do that in descending order. So to do that, we can just swap this entire stuff, right? And we go. So this is going to be hopefully in descending order. And after that, we can essentially just print first like top 10, right? And of course, it could be more, less than 10. We also should check if I is less than the count in here. And what we're going to be doing, we're going to be just like printing them. So nob log. So let's do nob log nob info top 10 tokens in S. So file path. And in here, we're going to do what? So a little bit of a space. And this is going to be SF. So we might as well actually do something like this. Then SFMT. And in here, this is going to be ZU. There we go. So I, then SV arg, frac items I, key, right? So this is the key, and then the value. Right, so the value is the count. The value is the count. So doesn't compile because why? So compares has no count because it's called value. It is called value. Anything else? So we have to provide nob info, and there we go. So the top is the. The top is the. That is absolutely poggers. And the second one is off. But it's within this small file. It's within this small file. All right. So, interestingly, all right, so we print the amount of size. So we can also maybe do nob log s. So let's do nob info. So contains ZU tokens. I think I removed that accidentally. I didn't really want to remove that, but I removed that anyway. So let's just do that because here we print a bunch of information about the file, right? So the size is this amount of bytes. This is how many tokens we found in here, and the top tokens is this amount of stuff. Yesu. So we kind of print the file name too much for whatever reason. I don't really know why, because obviously we're working with one single file as of right now. So maybe it makes sense to only print it once by saying something like nob. So here we extracted and we read the file successfully. So we can do something like nob info. And say analyzing S, and we're going to do file path, right? And here we can say, maybe we're going to even indent with 2 bytes size, this amount of bytes, then tokens, something like 1, 2 tokens, ZU tokens, so we don't have to provide the file path. So this size, where is the size? Yeah, we'll provide the file path. So let's actually quickly remove that. So I want it to look okay. And then here we can do top 10 tokens. We don't have to provide this thing. And in here we probably want to do actually a little bit more of that stuff. And there we go. So that looks cool. Even if we extend this code to handle several files, it's basically going to be several of these things, right? So several of chunks of this analysis. So size is this amount of bytes, tokens is this amount of tokens, top 10 tokens is that. Top 10 tokens is that. And yeah, so we need to be able to count how much time it took to do all of that stuff. So I think we'll need to have a function for clock. So clock, so I don't remember. So it was something like get, I think get time, yeah, that one. So get time, and the clock that we want to have is monotonic clock. Yeah, so that one. So let's go ahead and just try to do that. I'm not going to try to abstract away, because obviously this is a very platform specific thing. It's a very platform specific way of counting the time, but in my usual fashion, I just implement you know, the most dumb, the most like hard-coded way of the particular feature, and then when I'm done and it's working, I can factor it out, I can make it pretty, I can just like abstract it away and everything, right? So the first thing I do is I make a thing work, just work. It doesn't matter if it only works on one machine, on two machines, doesn't matter. Let's just make it work and see how it works in the entire application. Once we see that it works, we can start, you know, making it better. So that's how I like to do that. So because of that, I just like go ahead and straight up use platform-specific APIs, right? Obviously on Windows, it's not going to work, right? So Windows doesn't have any of this stuff. Monotonic, so this is a clock monotonic, right? So, and what we want to have in here, so we want to have this time spec, which is probably going to be begin, right? So this is the begin. Right. So in this entire thing, I suppose it may fail, by the way. So it may fail, but it will fail in a very strange situation, right? So if you take a look at the return, right, errors. So first of all, it may fail if you give it a pointer to an invalid address. Right, so here we allocate it on a stack and we give it here, so we know that it's not going to fail because of that. So yeah, we don't care about that specific thing. It can also fail when you provide an invalid clock ID. Well, we always provide a valid clock ID, so we don't care about that problem either. So it can also fail if you don't have permission to set the clock. So basically, in our case, it will never fail. Like it just won't fail at all. Like there's not a single error that will happen in our case in here. Right, so we know that the pointer is correct. We know that the ID is correct. And we're not using set, we're using get. So this thing only happens in case of a set. So in that case, we may try to handle it, but we may try to basically say, we just expect that this thing never fails. Like we just expect. That would make sense. All right, so, and then we probably want to do something like this, right? So after we did all of that stuff, we maybe want to get end, and in here, where is an assert? So we're going to put an assert in here, and this is going to be the end. We need to compute the difference between them. So time spec, right? Let's take a look at the time spec. So, and this is how many seconds we have, this is how many milliseconds we have, and so on and so forth. So, how can we basically compute the difference between them? So we have like two components in here. We can turn everything into nanoseconds and subtract one thing from another, right? So somebody says in the chat that I forgot a semicolon. Ah, okay. So, okay. So we can bring everything to nanoseconds, right? So, and then do the subtraction. Or if it's going to overflow, I don't think it's going to overflow actually. I don't think it's going to overflow. So I think it is totally fine if we just bring everything to nanoseconds, right? So I think that's totally fine. Or maybe we can even abstract that away, right? Maybe we can even abstract that away. So what we can say, print maybe log elapsed time, So we're going to provide begin, we're going to provide the end, and we're going to factor out this entire function, right? So we're going to do it like that. Struct time spec, struct time spec end. There we go. So next thing, we're going to have essentially a. So begin. What's the TV sec? And nanoseconds. Nano is 10 to the power of 9. It's 10 to the power of 9. So that means we have to multiply it by 1, 2, 3. So here we have 9 zeros. It's 10 to the power of 9, right? And then we add the nanoseconds. N sec. There we go. So in here we do b, and this is going to be end. And then we just basically subtract one thing from another, right? So we subtract one thing from another. and then we can print this entire thing. Though interesting, can we maybe use double in here? Is that something we can do? Just use double. So let me see. So we can call it double because it will make it easier to print. You know what I mean? It will just make it easier to print. So double, like so. Maybe we don't even have to do it like that, but maybe multiply it by. Yo, okay. Is that a good idea? Is that a good idea? Because then we can just do nob log, nob info. I didn't think about that. Elapsed time, and this is going to be long f, and here we can, yeah. Yo, is that a thing people do in C? Because I mean that's very convenient. I didn't think that this could be this convenient, right? So we just do everything in doubles, just in case we can cast that to double. Right, so all of that in doubles. Yo, chat, isn't that poggers? Isn't that I think it's poggers. Holy shit! So and here we can put sex, which means seconds, not what you thought. Sex, second. Anyways, so let's try to just build this entire thing. We're gonna be just building it. Look at that! Right, look at that. So expected some. The compiler just told me that I have to put semicolon, so I never have to remember about that. Isn't that cool? Isn't it cool that we came up with a special tool that reminds us that we forgot to put a semicolon, so we never have to think about it ourselves? Holy shit! This is the marvelous technology. It's cooler than ChatGPT. Holy fuck! Oh my god, this is so cool. I never thought this kind of shit is possible. Holy shit. Okay, so we also need to have like a clock get time. So let me see, clock get time. So we need to import this thing. So yesu kawai freaking desu. All right, so in here, look at that. It reminded us about semicolon yet again. Another semicolon, holy shit. And another semicolon, holy fuck. This is so insane. Oh my god. I'm feeling so productive. Also another semicolon. And another one. Okay, that's cool. Yesu, kawaii freaking this. Okay, so let's do run, and of course we have to provide the Shakespeare small, and yeah, it printed elapsed time. So maybe we should print elapsed time like after we did all of that. So we can actually print it at any point, right? So we can actually print it at any point. And to be fair, so let's factor out this entire stuff into a separate function and call it delta sex. It means seconds, okay? Right, so can take this thing, right, and we're simply going to return the delta in seconds. Delta in seconds. That's why it's called delta sex. That's why it's called delta sex, not because what you thought. Right, so let's do nob log, nob info, elapsed time, lf sex, delta sex, begin end. Boom. Let's run it. And so it took 3,300 milliseconds. So that's how much time it took. 300 milliseconds, essentially. We can actually do something like this. Can I do like 3 in here? Yeah, I can. So Yeah, essentially it takes like a half of a second, like, yeah. So it's half of a second. Maybe we can put S in here. Yeah, so I think it makes sense to actually like put S. All right, that's pretty cool. That's pretty convenient. I think like for some reason I feel like I never thought about doing these kind of computations in doubles, but it makes so much sense, right? And using the scientific notation to like sort of turn this into a fractional part makes so much sense. Yeah, so it looks elegant in my opinion. It looks actually elegant. So now we can, as you can see, like measure the time, how much time it takes, and everything. So we can take this thing. Can I basically do? Yeah, I want to take a double of this file. I want to take a double of this file. How can I multiply this file by 2? So this is very interesting. So there is a utility in Unix called cat. You know why it is called cat? You know why it is called cat? Because it is designed for concatenating files. It is designed for concatenating files, not for printing files into the standard output, for concatenating files. The way you concatenate the files, you do cat file A, file B, and you redirect it to file C. So, and you concatenate it to files. Who said we can't actually provide the same file twice and then save it to Shakespeare small double? And we got twice of this file. So we just concatenated file with itself. We just used cat in the way it was intended, right? So the way it was intended. It was designed to concatenate files, and that's exactly what we used it for. Right. So yeah, now you know. Now you know. And now we can just try to run on a double, small double, and see how much time it will take. And it actually, yeah, so it takes twice as much time now, right? As you can see, it takes twice as much time. So, but this is only a linear search. This is only a linear search. How can we speed it up? How can we speed it up? So essentially, so the way it works, right, so you have a bunch of cells. Each cell has a key and each cell has a value, and there you go, you have a bunch of these cells. Every time you want to find a particular cell, you have a key. What you do? Okay, you start and go linearly, right, and you compare. Okay, is that the same key? Nah, it's not the same key, right? So let's compare it in here. Is that the same key? Nah, it's not that key, right? Is that the same key? Oh, it's the key. So, and then I increment this entire thing. And if that key does not exist, we have to go through the entire thing. So analysis is basically, you know, O of n squared. O of n squared. So it would be like better if we could, you know, find it quicker. Well, theoretically we can, without any hash tables, we can just sort by a key and use binary search, but this is a completely different topic, right? So it's a completely different algorithm, completely different data structure, but I mean, it's just like, it's essentially like you can have different solutions for the same problem, right? So it would be kind of cool if accessing, like finding a particular value in the array was as easy as just finding a value by an index, right? Just finding a value by an index. So if in our case, key was just an integer, right? So what if it was just an integer, right? What if it was just an integer? We could basically just allocate array of frequencies, right? So, and we have like 100 of them. And every time we encounter that key, we will just access that key as we just use that key as an index, right? We'd use that key as an index and we would increment this entire thing. Something like that. That would be cool. That would have been cool. But unfortunately, key in our case is a string, right? So we can't really, you know, use a string as the key. Okay. Can we? Actually, that's an interesting question. That's an interesting question. So what if we just pre-allocate a bunch of things, right? So what if we just pre-allocate a bunch of like frequencies, like thousands of them? All right. And essentially, when I wanna, for example, have a key hello, what if I take all of the codes of each individual character in here and just sum them up? Just sum them up, like just take a sum of this entire thing or something. Can I use that as the key? Can I use that as the key? But what if it overflows this entire thing? What if it overflows this entire thing? We can just take a mod of 1000, right? So of course we can say it's n, something like that. We can just take a mod of this entire thing. All right. But what if like something like sum hello equals sum world is the same thing, and I'm gonna point at the same sort of array in there. So we can try to resolve that. We can, for instance, have cells of linked list, and every time you sort of hit a collision, or you can add a new node in here. Or there is a better approach called open addressing. So essentially, basically, if they collide, take the next element in there. So yeah, that's basically hash table, right? So isn't it? So, and this particular function sum is called hash. So essentially people spend enormous amount of time analyzing and designing different hash functions that behave in a certain way, so you reduce the amount of collisions in here. Quite often people even design hash functions for a specific use case, for a specific application. And these kind of hash functions have even security implications, seriously. Because if your application is using a hash table, right, and the hash table is vulnerable, the adversary can come up with such an input that will force all of your elements into a single cell, into a single bucket, thus dramatically reducing the performance of your service, and maybe basically executing like a DOS attack, denial of service attack. So yeah, isn't that cool? Right. You can actually like perform like a denial of service attack of some website by hacking their hash function for the hash table that they use. Right. And I think there were examples like that, right? I think there were examples like that. So it's kind of interesting to see that in the wild. At least in the competitive programming community, it is still like a thing that people do. So there is a very cool website called Forces, codeforces.com, right? So it's a website for competitive programmers, right? And so people just solve competitive programming problems in there. And during the competition, during the contest, there is a very interesting phase when people are trying to hack each other's solutions. So essentially, somebody who solved the problem can look at the solutions of other participants and suggest an input trying to break the solution. And quite often people go for analyzing the hash function. If the solution uses hash table, they try to find vulnerabilities in the hash function and come up with the input that will force the hash table to put everything into a single bucket, right? And those break the solution. So I only know Russian competitive programmers from that site. Well, I mean, this website was created by a Russian, as far as I know. And there's also a lot of Chinese people there as well. Have you done competitive programming before? In 2011 and 12? Anyway, I sucked at computer programming. Same, actually. I never actually went further than semifinals. So even though I have this like a very old T-shirt, I really suck at competitive programming, honestly. I do like competitive programming problems. I like algorithms, data structures, but I don't like this competitive aspect of competitive programming, meaning the competition with other people and limited time that puts too much stress on me. And because of that, I'm not a good competitive programmer. But it doesn't mean that I don't like solving this kind of puzzles. I do like solving this kind of puzzles. I do like computer science. I do like algorithm data structure. It's just I can't withstand this additional stress that is put into these competitions, right? So, I don't know. It's pattern recognition for the most part. It is true, actually. It is true. So at some point, like, there's not that many interesting problems in competitive programming, to the point that, you know, most authors is just like rehashing the same problems over and over again with just different wording, and the, you know, adjusting the difficulty of the problem by obfuscating the description. So, and it's just like, it's like at this point you question, like, what exactly we're competing at? Are we competing at programming and problem solving, or are we competing at decrypting the problem? Like, what exactly, what's the competition there exactly? Like, it's just competing at pattern recognition. Yeah, exactly. Decrypting the problem is basically what I feel Advent of Code is about. Yeah, that's what it's all about. That's what it's all about. That's what it's all about. Okay, so let's actually try to come up with some hash function. Right, so let's try to come up with some hash function. How good we have a hash function will just a sum be, right? So let's do hash, and let's maybe accept just a thing. Maybe we could accept buffer and the buffer size, right? So we have a buffer and the buffer size, and in here we could maybe get uint32t, something like that. But maybe we could accept just like uint8t. So, and in here we can just take the result. So this is the result. We're initializing it with 0. Then we are iterating through each individual byte of this entire thing. So buffer size, something like this. And now we can just like add the buffer I in here. We can just add buffer I, but it would be better to cast this entire thing to uint. Right, so, and if it overflows, we can just let it overflow. Right, we can just let it overflow. And then we can return the result. We can just return the result. So it would be kind of nice to maybe not lose this entire solution. Right, I kind of like that I have this naive solution, so maybe it would be nice to put it to a separate function, right? So like a naive analysis. Naive analysis, we're gonna accept Nob string view content, right? So that's what we're gonna accept, and I'm gonna move all of that stuff in there, right? So this is the clock. Interestingly, how are we gonna accept all of that? So, because, all right, so this is the count. I might as well simply move this entire code into this naive solution, because what's gonna be the essentially output, the outcome of this analysis? The outcome of this analysis has to be like the top 10 of these things. Right, the top 10. And how we're gonna approach this entire thing? So where exactly should we include this stuff as well? Okay, so for now let's actually include. Like, I'm just thinking, if I'm gonna have several solutions, what's gonna be the common part between them and what's gonna be a different part? But since I don't have several solutions, maybe it doesn't matter, right? Maybe it doesn't even matter because, you know, like, I don't have enough information. So every time I'm not sure how exactly to approach certain thing, that means I just don't have enough information. It's that simple, actually. It's that simple. So here, do I have a return? I don't even have a return. So we have a little bit of a memory leak in here, but that's fine. a bit of memory leak. So I don't think it matters to solve it right now. So analyzing this thing, so then we create the content and then we do naive analysis of the content, and that thing should just, you know, solve everything for us. So this thing requires int, and yeah, so this is the naive analysis. And at any point I can just like disable this entire thing and try other things, and I can try other things. All right, so let me grab the iterator over the tokens. Let's grab the iterator over the tokens. So this thing just iterates the tokens. We can maybe take a look at first like 10 tokens. Like let's take a look at first 10 tokens. Nob log nob info. So here is the space, and we're gonna print sfmt sfarg token. So just looking at the tokens. Here are the tokens. Maybe we can even put that stuff in here. Nob log nob info space tokens. Just tokens. All right, so here are just tokens. We can take a look at their hashes. Can we take a look at their hashes? Can we take a look at their hashes? I think looking at their hashes is something interesting, right? So and our hash is actually very dumb, right? It's just a sum of the bytes. Yeah, so let's compute the hash. So it accepts the pointer to the buffer, right? So it has to be token, you know, items. It's not items, it's data, and then token count, right? And that give us the hash. And we can print that specific hash. And how can we print it? So let's actually print it somewhere u, and I want to print 8 bytes. So we can actually print maybe x, something like this. And right here is going to be like that. So, okay, so for each of these things, we're going to print the hash. So here are the hashes. Maybe we're going to even capitalize the x and put 0x in here to indicate that it's a hexadecimal. Right, so here are all of the hashes. And as you can see, they're basically different. They're essentially different. Does anything collide in here? I don't really think so. I don't really think anything collides in here. So, so that's pretty cool. So there is a little bit of a warning in here, and this is because hash accepts uint8. So we have to cast this entire thing to uint8. But apart from that, so this entire thing is the same. So at what point this kind of stuff starts to collide, right? At what point does it start to collide? So we can maybe even print the number, the index, the current index of the thing, right? So the current index, so this is 0, 9, and stuff like that. We can try to maybe pre-allocate some sort of an array of those things. So essentially, let's just allocate some sort of an array, maybe array of booleans, right? Maybe some sort of an array of booleans. So let's call it slots, right? So this is going to be something like this. Malloc. Right, size of boolean and multiply by some sort of an n, right? So this is going to be n, and we can put maybe 1000 of them in here, right? So there will be 1000 of these slots. Let's actually do memset slots size of boolean and n. All right, so what we're gonna have in here. So we're gonna basically initialize all of that stuff with false, and let's maybe see at which point these things will start to collide, right? So we got a hash, right? So we got a hash, and essentially I think it would make sense to also do mod n, right? It also would make sense to mod n, so the hash is within the range of indices of the slots, right? Within the range of indices of the slots. Right, if slots h is already taken, we can maybe print something in here, nob log, nob info, and 1, 2. So what should we print in here actually? That will be interesting collided 0x 08x at ZU, right? So at ZU, the H, and we're gonna put count in here. Right, we're gonna put count in here, and maybe after that we're gonna break out of this entire stuff. Yep. So every time if it didn't collide, we should probably just set it to true. Right, we just probably set it to true. Okay, so as you can see, it didn't collide, nothing collided in here. We can try to increase the amount of tokens, right? So we can try to increase the amount of tokens, 100 of them. Collided, it's kind of fun. It's so funny. Right. So that's pretty cool. So what exactly collided? Yeah, is and is. Okay, but this is because it already exists in there. Right. It collided because it already exists in there. So maybe and that's fine. This is precisely what we want to have in here. That is precisely what we want to have in here. So maybe we should turn these slots into frac kv, right? We should turn these slots into frac kv, and maybe we should actually have some sort of a boolean that indicates that this thing is occupied, something like that. So by default, all of that is obviously going to be just 0. And yeah, it would be better to actually take the size of this entire thing, right? So of this entire thing, and yesu. So now, what I want to do essentially, when we are sort of like placing, you know, a token in here, but maybe can I just use value as an indication of occupation? Maybe not. Right, maybe there is a key of that value, but with just a frequency 0. So maybe that's fine. Right, so maybe that's fine. So let's not do that. Okay, so here we have slots, and we can check if that's occupied. We say that it's collided. But I mean, if it's occupied and slots H key Nob SV equal key and token. If they're not equal, only then we say this is collision. Otherwise, it is occupied, right? It is occupied. It is occupied, and we probably want to populate the key with token and the value with 1. But essentially, if this thing is occupied, so I think we need to split this entire thing, right? I think we need to split this entire thing. So if it is occupied and a key is the one that we expected, the only thing we probably want to do, we want to just increment the value. We just want to increment the value. Otherwise, if it's completely different key, well, we collided. Something like that. No? Something like that. Something like that. So I probably need to spell it slightly differently. Collided. And there we go. So now it collided at 30. Right, so now this is a legit collision, and let's take a look at what kind of words collide. Often and there. Often and there. But apart from that, it's actually managed to work relatively well. Right, it managed to work relatively well. It was actually relatively quick. Right, so, and every time we computed the hash, we could literally access the element just by indexing it like it was an actual array. Right, not by linearly looking it up, but actually precisely just like locating where it is. Precisely locating. And what's funny is that this is basically the solution with the hash table, it is basically the solution with the hash table, except it just like doesn't handle collisions, right? If we had like a better hash function, maybe we could like analyze more of the tokens. How can we improve this entire thing? Maybe every time we add this byte, we could multiply it by some value. So basically we treat bytes as digits in some sort of like a positional number system. Like we could multiply it by 255 and it's going to be basically like a rolling window, but we can multiply it by something smaller, maybe even prime, like 7. Will it actually go further without collision? So with this kind of thing, it will essentially go only up until 30, but can we just by multiplying this thing by 7 make it go a little bit further? Maybe we can even, you know what, like multiply the result by 7 and add this entire thing, so it's just like sort of accumulates and rolls, right? So there's some sort of a multiplication involved. It's actually at 54 now, right? What if we just increase this particular number? 67 without collisions and everything. 19. Yeah, so actually 13 was a little bit better. Oh yeah. So we can analyze a little bit more of these things. And now if we take a look what exactly we're colliding with in here. World and ink all of a sudden. Who would have thought? World and ink. Can we multiply by something like bigger? I don't know, something super big. Nah, it doesn't really improve it that much. So yes. You can play with different functions. Quite often it's better to just use somebody else function, right? Somebody else function that is designed by somebody who understands how all of that works. Or maybe not. Maybe you can just come up with something that you're fine with. Maybe these kind of collisions don't really happen very often, right? Maybe they don't really happen very often. Okay, how do you even handle this kind of situation, right? So if you find an occupied slot and the keys are not equal, what you can do, right? So do we have this kind of thing? So there is a technique called open addressing, right? So there's a technique called open addressing. So, and essentially you hit a particular thing and this is a collision, the keys do not match and stuff like that. So maybe I'm gonna actually remove this entire thing so the keys don't match. You basically go to the next slot and check whether it is occupied or not, right? So essentially we also keep track of whether we occupied or not and check whether it's occupied. If it's occupied as well, right, and the key is the same, you get to the next one and the next one and the next one and so on and so forth. Right, so this is open addressing, sort of like probing and resolution of collisions in here, right? So, and obviously it is not as fast as just instantly locating by an index, right? It is not as fast as instantly locating by an index, but it's faster than going through the entirety of the thing. So you're going to be going through some of the things linearly, but not the entirety, right? You're going to have these sort of like chunks through which you're going linearly, but they're smaller than the entire thing. Right, so that's basically sort of like the main idea, so that on average it's going to be sort of like faster. Open addressing is good but not efficient. Yeah, but I heard that in the modern hardware it is better to prefer open addressing because of the cache, right? So essentially it reduces the cache misses, right? Because you just like linearly probing and stuff like that, and people probe not only linearly, right? So quite often they probe quadratically, right? So they go by +1, then +2, then +4, and so on and so forth. So they learn quadratically, and of course, if you go outside, you can wrap around and everything. So yeah, so there are different ways. So depending on like the nature of data right? So you may have different probings and stuff like that. So I suppose I want to make a small break because I ran out of tea, right? I ran out of tea. I would like to refill tea, and after that we're gonna continue working on that and see if we can actually come up with working hash table. What's funny is that this is a half of the implementation of the hash table, basically. This is a half of the implementation of the hash table. We do not resolve collisions, and we have a shady hash function. But I mean, that's basically hash table anyway. That's the essence of it. That's the essence of it. You have a particular key, arbitrary key of some sort. You turn it into an index, and you just access the element by index. It's not going to be perfect, and you just try to then, after you found an index, sort of like locate it more precisely. Just by taking the key and hashing it, you broadly, roughly locate the element somewhere in the memory, and with the collision resolution, you sort of more precisely navigate towards the exact element. Does that make any sense? Right. Yeah, I guess you can think about hash tables as two steps. Just broadly, just roughly locate where it is, right? Which is just hashing and finding by an index. And then with the collision, with the open addressing or something else, you precisely trying to actually find the actual thing. That's actually a very interesting way of thinking about hash tables, isn't it? Right. So you're not trying to precisely locate right away. And linear search is basically the hashing, but without broad, quick finding of the element roughly somewhere. Right. That's a very interesting way of thinking about it. In any case, so let's make a small break. All right, I'm back. So let's try to resolve the hash collisions and shit like that. Right. So essentially here we encountered a hash collision. So that means what we need to try to do. We need to try to go to the next element, right? So we need to try to go to the next element. So maybe we can do something like +1, right? And check the key there, right? We can check the key there. If the key is equal, right? If the key is equal, then we can do that. So though, since we have to kind of repeat this process over and over again, I have a feeling that we need to organize some sort of a loop. So essentially, if this thing occupied and, like actually not if, I'm sorry, I meant to say while this thing is occupied and the key is not equal to the actual key, what we do, we just increment the hash. We just look at the next one, and then the next one, and the next one. Okay, so that's pretty cool. So afterwards, if this thing occupied and the token is equal, that means we found it, and the only thing we have to do is to essentially increment it, right? Just essentially increment it. Otherwise, if we found that this thing is not occupied, we can just make it occupied, right? We can just make it occupied, and yeah, so that's basically how we can resolve that. That's the easiest way to go about it, I think. Yeah, that's kind of interesting. So, but we also have to be careful, right? Because we have a limited size of the slots, right? So when we increment this thing, we want to make sure that it wraps around, just in case, right? So we're going to do mod n. Right, I'm going to do mod n. We do mod n in here, right? We do mod n in here, and we do mod n in here as we probe this entire thing linearly, right? As soon as we find that something is occupied, right? So to be fair, when it's occupied, maybe we don't have to check for the key in here. Maybe we don't have to check. So it's definitely going to be occupied. If it's not occupied, it's that. So the only problem that can occur in here is when the table is completely populated, you know? When the table is completely populated, only then this a problem can occur in here. But I suppose this is probably something that we want to keep track of, right? Something that we want to keep track of. So let's actually create M, which is going to be basically the amount how many things are occupied. And every time we do occupied equal true, we increment one thing. So this is how many of them we have in here. So, and before trying to probe, if n is equal, well, I mean, yeah, maybe we can just limit the amount of times we can do this kind of stuff. We can say that essentially the upper limit is n. The upper limit is n, and we can just increment it by I. In that case, we can have a situation when the slot is occupied, but the key is not equal to what we expect in here, right? And this is where we can throw an error saying that the hash table got overflown, right? So it got overflown. So we can't fit any more things in there. We can't fit any more things in there. So let's actually do nob error. Table overflow. Is that a word you can say? Probably, I don't know. So I'm gonna return one in here. So yeah, so we tried to do that. We couldn't find anything, so that means we need to allocate more, but we don't have more. So we can only fit 1,000 tokens in here. And yep, so let's give it a try. Table overflow sounds neater. Yeah, okay, that's true. So let's try to compile this. It compiles, look at it. So Shakespeare, small txt, unknown subcommand. Yeah, I have to do run for this entire thing. And okay, it went through all of the tokens in here. It went through all of the tokens in here, and they seem fine, right? So far, hundreds of tokens it analyzed without any problem. We can try to print the table. So let's actually reduce the size of the table to maybe 500. Okay, so that's fine. What about 100 of things? Okay, so all right, so that's cool. It's less than 100 tokens. It's less than unique 100 tokens, and then we can just go through the entire slots, right? So through all the slots, so n plus I, and let's actually print them, right? Let's actually print them. So we can even do something like if slots I occupied, if it is occupied, we can go ahead and print this this kind of thing. So we need to print something like nob log, nob info, so slots. So how can I, yeah, so it makes sense to just do slots of the hash table, like so, and then we can do log nob info, boom. So, and how do we do that in a naive analysis? So we just do it like that, right, in a naive analysis. So here, this is I, so here we're gonna print the number of the slot. Then we can do slots I key and then slots I value, right? So this is how we can approach this entire thing. And there we go. So yeah, here are the frequency within our tables. So there should be probably some holes in here. We can indicate the holes probably like so. So essentially, let's just print this, right? If there is a hole within, yeah, within the hash table, so here it is. So nothing actually hidden here. Nothing actually hidden here. Nothing hidden here. and so on and so forth. It's not bad, actually, not bad at all. So we can try to reduce the size of the hash table to maybe 10 and see it overflow. Yeah, table overflow. So right away, table overflow. So essentially, at this point, we can try to write an analysis with a fixed amount of tokens and just try to adjust the size of the table so all of the tokens fit and nothing overflows. Yes. So usually when the table overflows, how people solve that? People allocate a new bigger table, and they just insert all of the previous elements into that table the way they insert in here. Right. So this is how they do that, essentially. In fact, we can probably, so we don't really use M, right? So I thought we'll need a count for M, but I think it's not really needed. So we really don't use M anywhere. We can try to abstract away this specific hash table, because essentially what we need in here is just the slots, the items, and the capacity, What's funny is that we can already use this structure, surprisingly, because we have items. Items already have key value and occupied. They already have count. They already have capacity. So we can just use this thing as the hash table. That is funny. That is kind of cool. So because we use the same data structure as the associative dynamic array into which we learn, like search linearly, or we can just interpret it as a hash table. Who said we can't do that? We can do that. Like, why not? I don't see any problem with that. Sure, let's go ahead and do that. But we probably need to sort of like have different functions specifically for hash tableness of this thing. So let me see. Frac KV. We need a function that pre-allocates these slots, right? That's what we need. We need a function that pre-allocates these slots. So I have in Nob a function di append, which basically operates on dynamic arrays in a sort of abstract templatey way, right? In abstract templatey way, without caring about specific items. Maybe we could have a similar thing, something like hash init, and you would provide the capacity, right? So you have to provide the hash table. We can call it ht, and let's call it cap. So this is capacity. Within this function, what we're gonna do? So let's actually create sort of like a scope in here. Right, if you're wondering what am I doing with do while 0, Google up the following thing in Google. C macros do while. Put that in Google and read the first result on Stack Overflow. If you're curious what it is, there's a good explanation on Stack Overflow. Okay, so what we're gonna do in here, so we're gonna have ht, and essentially we're gonna take the items and we're gonna make them something like malloc, right, size of this thing, and we're gonna allocate exactly capacity amount of elements. Right, so this is the first thing. Then we set the count to 0 and a capacity to cap. There we go. So, and this is how we will be able to allocate any hash table, not only the frequency one, right? Not only the frequency one. So hash init. Pretty cool. So that means, so here I don't have to do slots. I can just do something like freq kvs, and this is going to be ht. So initially 0, but then I'm going to do hash init ht 1000. There we go. So 1000, and maybe I also want to do mem set in here, right after I allocate this entire thing. So memset sounds like a good idea in general. So let's put it in here and put that stuff in here as well. Boom. Cool. So yes, so HT, we initialized all of that, and that's very good. That's very good. So the next thing we probably want to have a way to find an element. We need to find a way to find an element. So it's gonna be a little bit painful, but let's actually go to the compilation errors in here. So since we're named HT, there will be quite a few compilation errors because of that. So let's just go ahead and fix them, right? So here we have the N, and this is the capacity. So this is HT capacity, right? So this is the only things that we can use in here, right? So this is just that. What else do we have in here? This is HT capacity. That makes sense. Slots are HT items. HT, can you see what I'm doing here? You can't. Items, so this is that. HT capacity. HT items. HT items. Could have just done a replace, but I think that's fine. HT items, and here we just do HT items. Boom, there we go. HT capacity. HT items. So we're slowly evolving our hash table, slowly but steadily. HT items, there we go. Cool. All right. So, well, I mean, 1,000 of those things is an overkill for sure, but a welcomed one. Okay, so what if I get rid of the limitation in here? Can 1,000 tokens be enough to... All right, so table overflow, right? Because we have at least like 2,000 of those things. So what about, you know, 10,000 of these things? All right, so it is handling all of the tokens. Maybe we should not print them. Well, I mean, it definitely slows it down. So let's not print the tokens that we analyze. Let's not print the tokens that we analyze. And okay, so it just prints all of them. So what if we don't print the unoccupied things, only occupied ones? All right. Okay, so it managed to analyze the thing. It managed to analyze the thing. So the only thing we need to do in here, by the way, we need to collect the final results and sort them in a descending order. That's what we have to do. So yeah, so essentially this hash table just doesn't grow as of right now. It doesn't grow, it just collects the data. So let's go ahead, instead of like doing the slot stuff, let's create frac vcase and let's do like final, right? So this is the final thing. And if we find an occupied item, we're going to be just copying it inside of the final thing, yeah? Right? So nob da append, so this is the final, and we're just copying that specific element in here. And after that, we're doing that queue sort. Right, so we originally called it frac. Let's call it frac here as well, so we don't have to rename too many things. Right, so this is the frac. And now, after we've done that, we probably want to print top 10 in here. We want to print top 10. Okay, so let's go to the compilation errors. Frac vcase, isn't it KVs? God damn it. All right. So yeah, it seems to be working. So one of the things we probably want to do is to factor it out to like a hash table analysis, right? So we already have a naive analysis, right, that just uses the linear search. We want to factor this thing out into something else. How can we call it? Maybe just a hash analysis, right? hash analysis. And here we're going to accept Nob string view content, right? So we're going to accept that. And let's simply move everything in there. Let's just simply move everything in there and see how faster it is going to go. See how faster is it going to go. So I'm going to put it in here. Hash analysis content. Right, so we initially had naive analysis and then hash one. So I'm going to comment it out. This is going to be that. So let's go to the compilation errors, just the compilation errors. So here it returns 1. Table overflow. We can maybe return something like false in case of a table overflow. Something like false. And essentially, when we call this function, if it's not, we're gonna just return 1. Since it already logs the error, we don't really have to think about it too much. Right, so it just logs the error, everything's fine. So let's try to recompile, control flow reaches, so this one should return true, so basically successfully. So what do we need in here? We need to measure the time. We need to measure the time the way we measure it in here. All right, so there's going to be hash analysis. Right, so we can include the allocation of memory and stuff like that. So, and like so. So this is going to be and like so. Do we include the sorting and stuff like that? I think we don't. In a naive analysis, we didn't include the sorting, so I'm not going to include that stuff either. Right, I think it does make sense to not include that. And here is the final sort of like a summary of the situation. So here is the sort, right, and here is the summary. So we just print the tokens, right? So we just print the tokens. And the top 10 tokens and everything, right? So it seems to be compiling. Right, so as of right now, we can check the naive analysis, right? So let's check the naive analysis, Shakespeare, small txt, right? So it roughly takes, you know, from 300 milliseconds to 500 milliseconds, right? So, but on average it's 400 milliseconds and stuff like that, right? So something like this. So if we switch, and this is the result that we get, right? So it would be probably make sense to, you know what? Let's actually run them simultaneously. We can basically log what exactly is the analysis we're doing. Okay, so here we say analysis. So let's put that inside of all of these analyzers, right? Inside of all of these analyzers. So hash analysis, naive analysis, they all put that. They will need file path, right? So that means we'll have to provide this. So let's actually go to the compilation errors, like so. So file path, they do need the file path, so let's provide it. They need buff count, but I mean it's just a content count, right? It's the same, it's literally the same. And in here we're gonna just provide const char file path. What else do we have in here? So this is the content count, and what else do we have in here? So we have to provide the file path like that, the file path like that, and let's compile. Okay, so everything's fine. And let's go to the Shakespeare small unknown subcommand. Yeah, we have to do run. Okay. So, is the result the same? First of all, is the result the same? It is. It is the same. They match. So, linear search, 400 millisecond. Very dumb hash table. Very dumb hash table. Wrong hash table. Implemented by the worst programmer on planet Earth who doesn't know what the fuck they're doing. Worst hash table, like worst hash, like just sum of the bytes. Just sum of the bytes. Let's actually take a look at the sum of the bytes. Wow. That's actually worse. Oh, this is so cool. You can literally see that. like hash that is just sum of the bytes is 500 milliseconds. I didn't expect that. I was expecting that it's gonna be okay, but apparently just summing up all of the bytes is worse than linear search. What the fuck? Like, if I didn't do this bad hash, would we ever discover that? What, like, how? This is worse than linear search. But if you just add a little bit of the stuff, if you just make it a little better, like maybe 31, somebody was suggesting 31, it becomes like magnitudes faster. Magnitudes faster. Too many collisions, yeah, probably. That probably creates too many collisions. This is so fucking cool. So, yeah. This is so interesting. This is so fascinating. Holy fuck. And what about the double? Right, so we actually doubled this file. Right, we actually doubled this file. And yeah, so this is the difference. Almost a second, 13 milliseconds. So it's just like in a very bad hash. Very bad hash. Very bad hash. Yeah. That's kind of... And now I'm pretty sure, I wonder if that hash table can handle the full file. So these are small files. These are small files. So, if I just do the full one, so T8. So first of all, linear one will take forever to do that. Linear one is just like going to take forever. So maybe we want to get rid of that. Maybe we want to get rid of that. So let's not do linear naive one. Let's do the hash. And the hash probably gonna overflow. Yeah, exactly. So that's the problem. So let's just try to increase the initial size. So it's 10. So what about 100? Okay. For damn hash, it took the same amount of time to handle full 5 megabytes as for the linear one to do the small one. That's actually very cool. Yo, this is so fun, I love it. So interestingly, there is a better hash function. So quite often people suggest to use something like dbj2, right? So I want to see how that thing performs. Does it perform any better? So I think that's DGB2. Yeah, not DBJ. I can never remember. DJB2. DJB2. So it's this one. This is so evil. This is not only an image. Fuck you. I'm joking, obviously, but fuck you. That is evil, that is cool, that is funny, that is clever, but fuck you. Like, it's like you can't just copy paste it, like. I swear to God it was done intentionally. Like it. I just got trolled so hard. Like, what the fuck? Ooh, there was a source image just as, yeah. Okay. This is the most genius trolling I've seen in my entire life. Holy fuck. Anyways. So yes. So let's take this thing. So this one is going to be called dumb. So this is dumb. This is DJB2. DJB2. And let's go through the compilation errors. So Okay, so this is fine. Can we just do it uint32t? So this is unsigned long. I think unsigned long is uint32, and this one is u8t. uint32t. So what are we doing in here? That's kind of weird. Okay, so let's do this one as well. I hope it's gonna be fine. So implicit such. Ah, I see. Yeah, it doesn't like that I'm using assignment inside of the while, and it suggests to put extra parentheses to sort of indicate that I know what I'm doing. Okay, I see. Implicit declaration. Yeah, so now djb2. Right, is it gonna be better? So is it not called djb2? Too many arguments. Ah, yeah. So this one is gonna be buff size. And in here, I suppose, I mean, come on, let's just do it normally. Like, why does it have to be so hackish? Like, it's like, this is like C developers trying to show that they're cool. It's just like, look, I know all of these plus, post-increment, pre-increment stuff, and you don't know that. Fuck you, I'm a C developer. Why? It's 2023, everybody programming in JavaScript, nobody cares. So, come on. So, yeah. So, and essentially, what we can do in here is just buff I, and let's cast it to u32. Right, so that's what we can do in here. It's basically the same, right? It's basically the same. Yep, so unused variable, let's not do that. And is it better? Does it perform better? Well, it's below 300 milliseconds, right? It's below 300 milliseconds. Well, sometimes it's 300, but it's usually below. And djb2, if we just do something like dumb, it should be a little bit... Try dumb with 33 instead. Okay. So wait. So it's basically that, right? Wait a freaking second. Did they just reinvent djb? So djb2 is basically sum with multiplication by 33. Really? Okay. Well, I mean, there's also a little bit of initialization here. Okay, so they also initialize with something, right? And start is okay. So it's kind of funny. So let's remove that. Let's just use djb2 from now on. So that's our thing from now on. So yeah, I wonder if you increase the capacity, will it perform like better or faster? Let's allocate like 1 million elements. Right, so here we have that. Doesn't really perform better, but yeah. So that's pretty cool. You wrote ggb1. Really? This is ggb1? Interesting. Why I wanted to implement hash table that is accessed similarly to how you access dynamic arrays in Nob. Right, so you have this set of macros that are independent from specific types you're working with, because they're just, you know, take them from the context, right? So they essentially expect your structure to have items, count, capacity. They don't care about the types. They just like substitute this code and stuff like that. Right, so what we need to do in here, we need to come up with an operation that performs a search regardless of the types and stuff like that. So we need to have something like define hash find, and it should accept HT and the key. All right, and maybe even hash as well. maybe even hash function with which you are like doing all of that stuff. And inside of this macro, I want to put this entire process, sort of speak, well, on top of just being able to hash, we also want to be able to compare, right? We want to be able to compare. So maybe we also need to have equal, right? But with the macros, it is very difficult to return. It is very difficult to return elements. So essentially, maybe what you're supposed to do, you're supposed to pre-compute the hash. You're supposed to pre-compute the hash, and then you do hash find the hash table, the hash that you found, and this function will modify this variable, right? It will modify this variable. So then later you can do this kind of stuff if you want to, right? So later then you can do this kind of stuff. So maybe it will even do the like clamping of the capacity itself, right? But you also need the comparison. You also need to compare the keys somehow, right? You also need to compare the keys somehow. So that is not going to work. That is not going to work. So abstracting away this interface is a little bit difficult, especially considering that that you compute hash differently depending on the element, and you compare the keys differently depending on the type. So abstracting a hash table like that, like you do with the dynamic arrays, is a little bit more difficult. Right, is a little bit more difficult. I'll have to think about that, like how exactly I can have a simple interface that is similar to dynamic arrays, but yet powerful enough that I can just like use whatever types I want, and it's still type safe, right, and stuff like that. But I think today's stream was a success, I think, right? So let's go ahead and enable naive analysis one more time, and let's just try to analyze a smaller file so we can see the difference. All right, so that's the difference that a hash table makes: linear search and the hash table. But I'm pretty sure you can come up with a data that has a lot of collisions for that specific hash table, and it will force it to push everything into a single bucket, effectively resulting in the linear search performance. But you need to know the hash function, right? And you need to be able to have control over the input and stuff like that, right? It should be possible to craft a malicious file that will perform really badly on this hash table, like extremely fucking badly. Extremely badly, right? But I don't really know how exactly to do that because I'm not an epic hacker, but I mean, I know that it is possible. That's actually super cool. I kind of learned a little bit by just experimenting. So this is why I like to do these like dumb various solutions. And yet again, don't listen to these people, right? So like you're experimenting with something that you're seeing for the first time, and you're doing some dumb shit just to, you know, explore things. Like the same thing I was doing with the React. Like, has anyone you like here like remember the React stream? I was doing a lot of dumb shit, and the React people were like fucking triggered. But I was doing that intentionally because I was just like trying different things, like exploring the space of possibility, trying to expand my understanding of the thing. Like my advice to you, don't listen to these people, seriously. Like don't listen to them. Just do dumb shit, just explore, just experiment, and don't listen to these people. Don't listen to these people. These people who look at your code over the shoulder and start criticizing for, oh, your function is dumb, haha, I know better. They're very insecure. They're literally just looking for opportunities to elevate themselves over the other at the expense of other people learning things. Literally ignore them. Better tell them go fuck them. Better not, right? Just don't listen. Just like literally ignore them. The only reason somebody would look over the shoulder, look at your code and say, your code is shit, you have to use this hash function, you dummy dum-dum. The only reason why somebody would say something like that is because they're insecure. Like really, like an actual expert in the field who knows a lot about this kind of stuff, but doesn't feel insecure, they will never say anything like that to you. Even if they see that you're doing some dumb shit, they will go, oh, you're learning something. Okay, let me actually show you an interesting, cool thing. Let's try to do this different dumb shit and let's look at this different result. Like an actual person who's very confident in their ability would never tell you, you dummy dum-dum, you're using the wrong function. Fuck you, I know better. They will never say anything like that. Even if they know that you're doing something dumb, they will never tell you that you're doing something dumb. That is very important. Like if somebody is like looking on the shoulder and tell you, ignore them, they're insecure. That is very fucking important. Because if you let those people get under your skin, they will discourage you from learning things. It is very fucking important. It's like you won't believe how fucking important that is. Unless it's your mentor friends. Well, I mean, if they're doing that in a friendly manner, then of course, right? So, I mean, sure, if this is sort of like a friendly, just poking fun of each other, so that's totally fine. Right, but generally, just don't let those people to get under your skin. Just don't fucking let them do that. All right, so I guess that's it for today. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you all on the next recreational programming session. I love you all. Mwah!